Okay, welcome back, everyone. Hope you had a good weekend. So let's get started on reviewing what we were doing last time. We were considering a multivariable linear model where we have the target we're saying is approximately equal to some intercept term plus linearly scaled versions of our D different features. So this is an extension of what we did in the previous unit where we had a single feature and intercept, and now we have multiple features and an intercept. So now when we do our design, we're trying to simultaneously design these D1 coefficients in this vector beta. The other thing that's a little different is now we have a vector of features instead of a single one that we had in the last unit. So those are the differences. So if we now add the I indices, the I is indexing where we are in our training data set. We're saying that the prediction we make for the ith target, yi, is going to be this linear combination of the features for the ith sample, so xi1 through xid. And what we can do is we can stack those as well as the a 1 into this row vector and stack the betas into column vector. And now we have a row column type of multiply. And then that helps us to understand how we can express all of these together in a vector using a matrix that we'll call A, whose rows are constructed like this, and then this beta vector here. So when we do that and we stack all these guys together here, we finally get this equation, which says that the vector of predicted targets is equal to this matrix that contains this one column, but then all of our feature data times our coefficient vector beta. So that's what we do. That's the model we use during training. Now, we'll talk about how we get the least squares coefficients beta, but once we do that and we have them, we can then apply that to a new data sample that we're given after training. In that case, let's say we collect our features into this vector X. We can plug that into a row that has the same kind of structure as this, apply our coefficients to get a prediction for that particular set of features. Okay, any questions so far on this? Yes?
When we make a prediction at the end, do we want our model to learn from our predictions, or because we don't know the outcome, we wouldn't want to change our model based on predictions?
Yeah, we're not going to, in this course, we're not going to consider the idea of continually learning and changing our model based on new predictions. That is a branch of machine learning called online learning, but we're going to do something that's a bit simpler where we just have a training data set, and we're going to assume that when we use our trained models that we're using them on data that is statistically similar to our training data set. It's never going to be the same, and we're going to have to worry about the differences, and we'll worry about that units 3 and 4. But statistically, we'll assume that it's pretty similar.
Great, thank you.
Okay, any other questions? Okay, great. So now we can move on to discuss how we're going to come up with the coefficients beta. So basically, in Spirit, this is a direct extension of what we did in the last unit. So we're going to, so here's, just to say it again, here's the prediction equation. Here is the data that we're working with. We have XY pairs where I goes from 1 to n. And we would like to minimize the RSS. Maybe someone can take a stab at writing that down. So let's see, is Franklin Charles here? Okay. What about Brett Hinkle? No? What about Colby Hiralal? Okay, Colby, so what would that equation be for RSS? Do you remember how RSS is defined? It's the same as before.
The summation from I equals 1 to n of y sub I minus y hat squared.
Yeah, y hat sub I, that whole quantity squared. Good. So that is in fact what our objective is, to minimize this same difference between the target and our prediction, in particular the sum of the square differences across all of our data samples. And one thing that changes a little bit is the visualization of it. So in this case, when we have more than one feature or more than one of these slope coefficients, instead of having a regression line, we actually have a regression plane, or you could call it a hyperplane, which would be a plane in dimensions greater than 2. But this picture here on the right, this shows it shows an example of a regression plane when d is 2. In that case, you have x1 and x2 being your features. And you can see y on the vertical axis. And so now the plane has basically 3 degrees of freedom. You can shift it up and down. That's controlled by beta 0. You can tilt it along the x1 axis. Change the slope on the x1 axis. That's controlled by beta 1. And then you can also do this along the x2 axis. That's controlled by beta 2. So 3 degrees of freedom in this case. In general, when you have d greater than 2, we can't draw a nice picture anymore. But geometrically, it has all the same properties, so the intuition holds. In that case, we have d plus 1 coefficients total instead of 3 like this. And so our goal is to make the differences between these dots. So these dots are like our xi, yi pairs. Those are the black dots. Make the differences, or the square differences between the dots and the plane minimal on average over our data set. So similar in spirit, just a generalization. All right, any questions on anything here? Is this making sense? Okay. Oh yeah, sure.
So if you have more independent variables, in a way, this figure would be like 3D, 4D.
Yeah. So this would be like, you could say the 2D case where d is the number of features. And then there's a 3D case where if you have 3, x1, x2, x3, there's a 3D version of this. It's hard to visualize. There's a 4D version all the way up to any finite number you can imagine. So yeah, different data sets will have different numbers of features. Okay, great. Any other questions? Okay, so sometimes we would like to write this in a bit more of a compact way, and we can do that using the norm. So here's RSS again, and let's remember how a norm is defined, or at least how the Euclidean norm is defined. So if you have a vector x with coefficients xi, then the way that you define the Euclidean norm is you have those coefficients squared, you sum them up, and then you take the square root. Actually, let's not use I here for the subscript. Let's use J, because J is the variable that I'm going to typically use across the different features, whereas I is across the different data samples. So here's a visualization of this in the case. So maybe I'll even go further and I'll write this where we have D, and then the visualization here is if you have D equals 3. So this is a point in 3-dimensional space, and that point is described by its locations on the 3 axes, x1, x2, x3. And if you would like to know how far that point is from the origin, and you'd like to describe that using the Euclidean norm, you just take the square root of the sum of the squares, and that tells you the length of this line. That's essentially what the norm is. The norm is the distance from the origin, or you could say the length of the vector. There's different norms. For now, we're just going to use this Euclidean norm or L2 norm. We'll get into different norms later. So this is the standard norm people use for finite dimensional vectors like this. Okay, so given that, how can we write RSS here as a norm? So let's see, is Shengzhe Tan here? Yeah. What about Robert Straveler? What about Levi Waldron? What about Jack Wenzel?
Did you say Jack Lanza?
Wenzel, Wenzel. No. About Maxwell's XUN? Okay, so yeah, how do you think we write RSS as a norm?
It would be the squared norm of yi minus yi hat.
Well, so I guess the difference, so here we're using a sum and the individual i's, and with a norm, the sum is kind of already embedded inside the norm. So that means we wouldn't want to talk about the i's individually anymore. So the norm is operating on vectors, whereas the sum is operating on scalars.
So it would just be y minus y hat.
Exactly. So we're going to have a, y vector. I'll denote that with an underline minus y hat. And yeah, importantly, the norm here is squared because we want to get rid of this square root. Okay, so this is a more compact way than to use a sum. This is very frequently written this way. And yeah, it's concise. It helps, once you're familiar with norms and you see this, you immediately understand it in a way that is a little more complicated if you look at the sum. There's just more going on. Okay, any questions on the norm? And actually, we can even go one step beyond this. What if we wanted to write this not in terms of y hat, but in terms of the features and the beta coefficients? Does anybody know how we could do that? Yeah.
B minus AB.
Yes, A matrix times beta vector squared. And how we got that is we have to just go back somewhere a few slides ago. We wrote y hat this way. So that's essentially, we're just plugging in that definition of y hat. And the nice thing now is you can see that how the RSS explicitly depends on beta. So this will be how we can figure out how to minimize this RSS. We can basically attack this norm directly. Okay, great. Any questions on this? All right, so essentially we're doing that same general machine learning recipe, 4-step procedure. We start with a model with some parameters. In this case, we have a multivariable linear model. We get a bunch of training data. In this case, we have that diabetes data in the demo. Choose a loss function. In this case, we've chosen RSS as our loss function. And finally, the part we haven't quite done yet is find the parameters, the betas that minimize that loss. So we want to find the beta that minimizes our RSS. So that's the part to do next. Okay, so we're going to use the same approach as we did before. We have a quadratic problem, essentially. It has a particular form like this. And we're going to get into these details in a future unit, but this is what's known as a convex and differentiable cost, and that means that if we find the betas that set the gradient vector to 0, and we solve for those betas, we will have found the minimum. So again, the intuition is that if you look in any of these coordinate axes, when you're at the minimum, the slope of the cost is 0. So we want to find the point where the slope is simultaneously 0 in all directions. This is our gradient vector. So we have, actually, I think there's a small typo here. This should start with beta 0, not beta 1, because beta 0 is one of our coefficients. We want that derivative to go to 0 as well. But basically, yeah, the gradient vector is just the vector of partial derivatives over all the coefficients in beta, starting with beta 0, then beta 1, all the way to beta d. So that's our approach. Find the beta, the 0 is the gradient, and that will be the solution to our problem. That will minimize our RSS. Okay, any questions? Okay, so now we have a little bit of work to do, a little bit of linear algebra. So this is our RSS described using the summation in terms of y hat. We can also express y hat this way. Let me try to unpack that a little bit. So we saw on the previous page that we can make the y vector as, can write the y hat vector as the A matrix times the beta vector. And so what we're interested in now in doing is looking at the ith coefficient. And so if I want to look at the ith coefficient here, that would be just one element. I would get that by taking the ith row here and multiplying that times this whole vector. And if I want to write this inner product, this times this, in terms of a summation, that would be this. So what I'm doing here is I'm using j to index across those columns, as well as using j to index down beta. And so I get exactly this for this element. So this is like similar to, I think, what you saw on some of the homework 0 problems, right? Doing this sort of stuff. So hopefully now that you see this in the lecture, it's not too much of a stretch to understand it. Are there any questions on how we went from here to here? Is everybody good with that? Okay. So, so now that we have things this way, the reason why this is convenient is we need to compute all these different partial derivatives. And once we got it into this form, we can do that with just basic calculus. If you leave it in the vector form, like this, and you know enough vector calculus, you can do it directly, but I'm assuming you guys aren't there yet, so it's my recommendation in this class to always get it down to scalar variables before doing your calculus. That's just going to be a lot more successful. Okay, so this is what we need to do. We need to evaluate these quantities, and we need to, in fact, set them to 0, and then solve for the beta vector that sets them all to 0. So we'll just look at a generic partial derivative for the jth element. And so if you remember, we do this using the chain rule. So we'd like to take the partial derivative of this with respect to beta j. So the first step is to remember that because differentiation is linear, we can actually move the derivative through the sum and then just focus on differentiating this part. Okay, so when we differentiate this part in the square, we use the chain rule. So we get 2 times this whole thing, which I'm writing this way, just in a slightly more compact notation, y hat. So 2 times that times the derivative of, partial derivative of this with respect to beta j. Okay, now here, things get a little bit tricky. This is a very important thing I'm about to say that confuses a lot of students. So over here on the left, we're looking at a particular j. So for example, I'm just using j as a stand-in for a particular partial derivative index that I want to look at. So maybe j is 0, maybe j is 1, but j is like some fixed number. However, over here, this j is being used as a temporary variable just to execute that sum. So I'll write temp variable. And in fact, you could substitute in any other temporary variable for j as long as it doesn't conflict with something else that you've already defined. You wouldn't want to use I because we're already using I for something else. So the problem now is that if you leave this as j and then simultaneously over here use j to mean something else, you get nonsense because you're using the variable j to mean two completely different things. So this trips up a lot of students. So what I'm saying is, when we come to doing the partial derivative of this, we need to change the variable j because we're already using it to mean one thing over here. So we just need to change it to something different. And the way that I'm changing it here is I'm just putting a prime on it. I'm just calling it j prime. So now j prime is a new variable, not to be confused with this j over here. Okay, so now that we've just rewritten this in a less confusing form, we're ready to go to work to compute this partial derivative. So essentially we want to compute the partial derivative of this minus this with respect to beta j. You can see that the first term does not depend at all on beta j, right? So the partial derivative is 0. And then we have the second term. So I want to compute the partial derivative of this with respect to beta j. So the thing to remember here is that this is just sort of shorthand notation for the sum of all these different terms. So for example, it's like ai 0, beta 0 plus ai 1, beta 1 plus dot dot dot, all the way to aid beta d. Okay, so this is just shorthand notation for this thing. So now I'm looking at a particular beta j. I want to take the partial derivative with respect to that. That's going to be one and only one of these terms, right? So there's going to be, in particular, it's going to be the term where j prime is equal to j. So maybe that's, for example, maybe if j is 1, that would be this one, in which case all these other terms here, they don't contribute to that partial derivative because they don't depend on beta j. So the only term that's left is the one that depends on beta j. And so for that term, that has the form aij beta j. When you take the partial derivative with respect to beta j, it just becomes aij. Of course, you have this as well. So let me just write this down and then come back for questions. So we have the sum here on the left. We have the 2 on the left. We have the minus sign from here. And now we're going to have this part. This is going to be yi minus y hat I. And then finally, the partial derivative of this with respect to beta j, which is going to be aij. Okay, so this kind of computation is going to show up over and over again in the lectures, in the homeworks, on the exams. So it's super important that you understand all these nitty-gritty details. Question?
So how I should understand why you change from J to J prime is that J is just all the data entries in IPRO from J to 0 to J, but J prime is that specific entry in that IPRO.
It's swapped. So you have the right explanation, but
Okay.
j and j prime were swapped. So j, on the left side, we kind of said, I want to look at the partial derivative with respect to the jth entry.
Okay.
And j is there, it's like some fixed, it's the 0th or the first or second. But then meanwhile, here, we're trying to express this in a more compact form. And so we express it as a sum, and we can choose any variable we want here in place of j. So when we said it first, there's no problem with using J itself because J had no other meaning. But when we come down here, J is already taken. That's already has a particular meaning. And so the temporary variable used to express the sum, we can use anything as long as it's not J or I. So there I'm using J prime. I could have used K or whatever you want. But that's why we did that substitution. And now it's very clear when you come to do the partial derivative, there's no clash between this J and that J. When you have J here and J here, it's not even really clear what that means because it's like J is being used to mean two different things. It's sort of illogical. So
J on the bottom is just that particular index.
yeah, and that's inherited from this,
Got it.
right? Yeah. Great. So is this making sense to most people? I do want to stick on this until there's no questions because it's so important. Yes.
Does that particular beta J come from whenever we were looking at the gradient of RSS, which entry and vector we're at?
Yeah. Eventually, so we want to need to do this for all the J's, and we're kind of exploiting the fact that there's a similar structure across all the J's. So I can once I do it for an arbitrary J, I kind of get it done for all of them. It's not like when I go from J equals 0 to J equals 1, like I have to rederive things. So I can be just generic and come up with this expression. This holds for any J equals 0, 1, all the way up to D. Right?
Thank you.
Sure. Okay, so that's what gets us here. Let's see, this should be a D. Okay, so that's what gets us to this point. Are there some more questions I can answer about how we got there? Everybody's good with that? Don't be bashful because usually if one person has a question, then other people have the same question. So you're actually helping everybody by asking the question. Okay, so if we're good to move on, then we can move on. So now we have the answer that we want written in the form of a summation. We actually want to bring it back to the world of vectors and matrices because that's going to make our lives easier for the next step. So the next task is to write this summation in terms of vector matrix quantities. That, again, was one of the things that you were practicing back on homework 0. And so that's our current task. We know that these AIJs, this is in particular the ith row and jth column of our big A matrix. And we know that yi is the ith element of our y vector. Y hat I is the ith element of our y hat vector. And so we can basically, rewrite this in terms of those quantities. So here's a visualization on the bottom of how we can do this. So if we think about this quantity, this matrix A transpose times this, you can see that when you look at these entries, as we go across the columns, we're actually indexing across our examples, our samples in our data set. So when you see n, you know that that dimension is the sample dimension because we have a total of n samples. If you go down this way, you see D here, that's the clue that, this other dimension is indexing through the different features, like blood pressure, body mass index, and so on. So this direction, we typically use J for that variable. And then as we go down y and y hat, again here we see n, so we know we're coming across the examples in our data set. When we set up a matrix multiply like this, we have to use a common index for that matrix vector multiplication to be valid, right? Like if this gets transposed and you had J going this way and I going that way, that's just not set up for a matrix vector multiply. You have to have I going across this, and now, now you have a valid matrix vector multiply. All the dimensions will work out correctly, and that is exactly how we're getting this over here. So the other way there's several ways to think about it. I recorded a short little video for homework 0 that I put up that explained this another time, but essentially if our goal is to translate this into a matrix vector equation, what I always do is I just start drawing some little pictures. So in this case, one way I could do it is I could say, okay, let's make this matrix A. So the way A is defined, we have I coming down the rows, J going across the columns. Now I need to do a summation across I with this other stuff. So that means that that vector must live here on the left, because that is where I have I matching this I. So this vector on the left, this would be the vector y minus y hat. So I'm looking at the ith entry of that vector. And finally, at the end of the day, I'm looking at a very specific value of j, the one that I have chosen when I wrote the left side of the equation. And so really I'm looking at this vector, but I'm looking at the jth entry of that whole vector. So essentially, when doing that, I'm kind of implicitly looking at the jth column here, but I think it's a little bit easier to say I have a whole vector here and I'm extracting the jth element. Okay, and the last way that this can be connected to this expression over here is that if you have a quantity like y minus y hat transpose, oh yeah, I guess to be clear, this has to have a transpose on it, because without a transpose, that must be a column vector, because that's the way we always define our vectors. So to make it a row vector, put that explicit transpose on it. Okay, so what we have above is this. And now the question is, well, how do you get that into this form? You exploit the fact that this is a scalar. If you have a scalar, that's like a 1-by-1 matrix, you can transpose it and nothing happens, it's identical. So if I want to transpose that, I can write that with an equality. And now I want to transpose this whole thing. So it's essentially like this is some row vector that I'm taking the jth element out of. I could also make a column vector, take the jth element out of that. So to transpose this, what do? We transpose the individual pieces, but then we swap their order as well. So we get A transpose on the left and y minus y hat without the transpose, because transpose of a transpose is like no transpose, and we finally get this. Okay, so this is another way to see, just an approach to get to this point. So again, I have a longer video, like a 10-minute video on showing how to do this for a couple problems, if you ever want to come back to this method. But this is the sort of way that we'll be thinking about things all semester. We'll be doing a lot of this stuff. Okay, is everybody okay with this expression then? Okay, any questions on this? Okay, and then the last step is easy. Just like on the previous page, we can substitute in for y hat a times beta. And so now we finally have our expression for this partial derivative stated in a very convenient form. And finally, the thing now to remember is that we actually want this thing we've derived, we want that to be equal to 0 at all the indices j. So to put it another way, we want this, for every index j, we want this vector to be 0. That means we want the entire vector itself to be 0. So finally, we can rewrite this as just simply A transpose times y minus A times beta. This is going to be, I'm going to distinguish it as the least squares solution by putting a little ls there. And notice that this equals a bold 0, which means a whole column of zeros, 0 vector. If we want to expand this, we could do that. So this is like A transpose y minus the quantity A transpose A beta least squares. And now, from here, we can bring this to the left side of the equation, after which we get this. And we're almost there. The last step is extracting beta from this equation. So let me see, is Seth Aldridge here? Yeah, so how do you think we can make the final step and write an equation for beta least squares?
Multiply on both sides by A and A transpose.
Yeah, multiply on the, okay, so we do want to multiply on the left by a matrix that will essentially cancel this. We want to cancel that. We can do that by multiplying by its inverse. That turns this into the identity, which is like, nothing essentially. And then we will have beta least squares. So we need to multiply on the left by A transpose A inverse. We do that on both sides of the equation, and so the right side turns into this. Yes, question.
Why couldn't you have canceled off the A transpose earlier by
Yeah,
multiplying?
that's a great question. So, yeah, the question is, and this is, I think, how it was originally answered. As a first step, could we not just do like multiply by A transpose inverse on the left? The answer is no, because there's a couple things that we need to have a matrix inverse. So we need the matrix to be invertible. A lot of matrices are just not invertible. There is no such thing as the inverse. So a minimum requirement for a matrix to be invertible is that it's square. In general, the A matrix is not going to be square. It's usually going to be tall. Sometimes it can be wide. In very rare cases, it might be square, but almost never will it be square. So because it's not square, A or A transpose on its own does not have an inverse. However, A transpose A, this matrix, is going to be square. So for example, if A is tall, then just to draw a little picture, A transpose would be wide, A would be tall, and you do that matrix multiply and you get a square matrix of that size, right? That's the typical case in machine learning. So the typical case is you have many more examples than you do have coefficients you're trying to learn. And that's certainly the case like in our diabetes demo. I'm trying to remember how many samples. I think it was like 400 and some samples, and it was maybe like 9 or 10 coefficients we're trying to learn. So, the number of knowns is like 50 times the number of unknowns. That's the normal situation. So that said, we still are making an assumption when we want to do this step here. We are assuming that the inverse of this matrix does exist. And it does not always exist. So one case where it will not exist is if this A matrix is wide. So if A is wide, then, so let's see. So this one I'm drawing here, this is A transpose A. If A is wide, then A transpose A looks like this times this, which is a big matrix like that. But it turns out that that matrix will not be invertible. And so this approach fails. We will need to come at it with a different strategy, and we'll talk more about that later. So this approach fails in particular when the number of samples is fewer than the number of features. So again, in this case, this A transpose matrix will have, let's see, the A matrix A matrix has D plus 1 columns and n rows. So when n is small, that matrix is wide, and you run into this invertibility issue. There's ways around it, but it's just not obvious how to do it at the moment. Okay, so that's what we have finally. We actually now have an expression for our least squares coefficients. We know how to design them. So we solved that problem. Are there any questions on the derivation on this page? Is this pretty clear? Everybody good at this? Okay. Seen a lot of blank stares. I don't know if that means that you're lost or if you're good. So everybody's good? Okay. Another question we could ask is the same we asked in the last unit. How do we know whether the predictor is doing well? So it turns out this slide is identical to the one of the last unit. We're going to use this normalized RSS. We're going to first divide by the number of training samples. We're going to divide that by the variance. And as a result, this new quantity will be interpretable for any number of training samples or any size of the targets. But that's what people usually do is they go one step further and they subtract that thing from 1 to make r squared. And then we talked about how r squared equals 1 means we have perfect prediction. R squared equals 0 means we have a predictor that's no better than the trivial one that ignores the feature data x and just approximates y by its sample mean for, in all cases. And if you have a negative r squared, then you're doing even worse than that. So r squared is the same. But coming back to our least squares solution that we just derived, you might say it's a little bit complicated. It's not exactly clear how to interpret it. So what I think makes it difficult is that you started with this matrix of features here, the feature data, but then we added this column of ones. So now we have something more complicated. And then we're doing all this complicated stuff. We're transposing it, multiplying it, inverting it, transposing it again. Like, it's hard to really get a lot of intuition out of this operation. So, so it's not very insightful. So the question is, can we rewrite this in terms of sample statistics similar to what we did in the last unit, and maybe get a bit more meaning out of it that way? Okay, so that's what we're going to do next. So to make that task easier, we're going to rewrite this just a tiny bit. Essentially, we're going to leverage the fact that beta 0 is a little bit different than all the other beta coefficients in that beta 0 is not multiplying any feature x, whereas all these other betas are. So that means maybe we should treat beta 0 a little bit differently in our derivation. In particular, what we're going to do is we're going to take our vector that contains all these coefficients and split it into two parts. The very first coefficient in that vector is obviously beta 0, but then we're going to come up with this new name for all the remaining coefficients. The notation is sort of borrowed from what you see in MATLAB and NumPy and stuff. This beta 1 through d, basically we're using that to mean a vector constructed from beta 1 through beta d that is omitting beta 0. Okay, so we're just basically looking at all but the first coefficient in the beta vector. So that's what's new here. And with this notation that we've just developed, we can write this, we can write y hat a little bit differently. We can write y hat as beta 0 plus this new vector, beta 1 through d transpose times our x vector. So now you can see how this new vector operates directly on the x vector, whereas the first one is just like an offset. Okay, so we're doing this to make our lives easier because we can, the next step will be to come up with some statistics for x. Those will involve these, or will interact with the beta 1 through d coefficients. whereas the beta 0 will, as you see, it's not multiplying by any x, so it doesn't interact in the same way. Okay, so is everybody good with what we have here? All right, so let's move on to our statistics. So we're going to repeat what we did in the last unit, but now we're going to do it with vectors. So the first thing is the sample mean vector. So we have, so this is our definition. So these are d by 1 column vectors, right? So what we're doing is we're just averaging over all that set of vectors, and we're creating a new d by 1 vector here called boldface x bar. So that's going to be the mean vector. So what happens if I look inside that vector? When I look inside, I look at the first coefficient. I'm writing here as x bar 1. What's the interpretation of this x bar 1? Beyond just being the first element here. Is it some statistic of our data? So what do you think? So this is in fact the sample mean of the data xi1, sorry. Yeah, I guess this is the best way to write it. xi1, where I ranges from 1 through n. So this is all the examples of the first feature from our data set. So if I just, this is like something similar to what we had in the last unit. If I just look at the sample mean of these guys, these are scalars, I would call it x bar 1, and that's exactly what is the first element in here. Okay, so this is definitely connected to what we saw in the last unit, and then we go down this vector and we pull out the sample mean of the second feature, sample mean of the third, and so on. We go all the way down. Our targets remain scalars for now, so those are exactly as we defined them before. Any questions on this construction here? Is this making sense? Yes.
So then x1 would be like a vector? Sorry.
So yes, so in this case, xi when I equals 1, this is the first data sample, but it contains all the different features. So like blood pressure, body mass index, those would be the entries in that vector. But this is just for the first patient. And then when you do I equals 2, that's all those things for the second patient, and so on. So this average is like across patients in the case of our diabetes data set. So like the first element here would be, if body mass index is the first feature, this would be the average body mass index across all our patients. Okay. Good, yes?
Is that also equal to the ith column of A, like the big matrix A?
It's closely related to the ith row of A, because so for example, this is the nth row of A, and you can see it has the data for the nth patient. The only difference is that A has this additional intercept 1 in there. So you know, xn, boldface xn would be this. Yeah. In fact, we sort of defined all these quantities back here. Oh, no, where was it? It was way at the beginning. Here's where we started talking about that stuff. So this is for that ith patient. You know, that would be the ith row in this X matrix. Okay. All right. Good. So any other questions on the sample mean? Okay. So now the next thing we can do is we can generalize the variance to what we call the autocovariance matrix. So the thing to remember here, or the thing to notice here, is I have the ith sample minus its mean. That's going to be column vector. And over here I have the same thing but configured as a row vector, that transpose. And so when you do this, you get a matrix, a square matrix. And when you look inside that matrix and you look at this first element, this will be the sample variance of that same data set. The first feature across all the patients. Because that is going to be this element times this element averaged over all that will give you this first row and column of that matrix. Now, if you look at the next element on the diagonal, that'll be the sample variance of xi2. And so on. As you go down the diagonal, you get the sample variances that we saw before. But what's different now is we also have things, off the diagonal. So when I go down here, I'm really talking about the covariance between the first feature and the second feature. I'm looking for how they are related. What is their correlation? So that's what you get off the diagonal of this matrix. So how the different features correlate with each other. Okay, so just to remind you, this is the expression we had for variance in the last unit, where everything was scalars. So all we're doing now is we're replacing these scalars with the vectors that we have now, and this whole thing becomes a matrix. But we can still relate the elements along the diagonal back to these variance quantities for the individual features. Okay, so is this making sense, the autocovariance matrix? Okay, and then the last thing is, how do our features correlate with our single target? So for that, we have this expression. It's now a vector SXY, which is a direct generalization of the previous covariance, where in that case, X was a scalar, so now X is just vectors. And so this will give you a vector times a scalar that equals a column vector. The number of coefficients there is the same number as we have in our X vector, which is exactly D. So here, this is a D by D matrix. Now we have a D by 1 vector. And when you look inside this vector, you can relate it to the scalar statistics. So the first element will be the correlation between x1 and y. The second one will be the correlation between x2 and y. Down to the correlation between xd and y. Not correlation, sorry, covariance. Okay, so we call this the cross covariance vector. It relates our features to our targets. Okay, is everybody good with these definitions? Okay. We can do something really similar to what we did last time, coming up with some alternative expressions that are useful for derivations. So if we start with our variance expression and we expand this quadratic, we get this xi times xi transpose thing, averaged. Then we have the cross terms, let's say x bar xi, but those get averaged over i's. So that gives you this. You can pull out the x hat because it does not depend on I. And what remains over here, does anybody see what that is? That's our x bar, right? So that's x bar, and then that gets transposed. For the next cross term, we have xi, x bar. So here's the xi, here's the x bar, transpose. So once again, That sum gives us x bar. And then finally, we have x bar transpose like this. When you average it, it's always the same element, so it just, the average goes away. And so finally, when you look at this, you have things that cancel. You have a minus x bar transpose, another minus x bar transpose, plus the same quantity. So finally, you have the first term minus x bar transpose. Okay, you can do something similar with cross covariance. Again, you expand this out into the 4 terms. Now you see that one of these terms simplifies down to y bar. Another term, like above, simplifies down to x bar. And then the last 3 terms are all variations of the same thing. So the whole thing simplifies down to the first term minus x bar vector y bar. Okay, so these are useful expressions for alternative expressions for those quantities. And we do have a little bit of derivation to do, but I think we can tackle that on Friday. This is a good time to stop. And if you guys have any questions, come up to me now and ask. Otherwise, see you guys on Friday. By the way, on the lab that's due, I recommend starting your lab early because this is your first time. You're trying to get your GitHub set up. You're trying to get your Colab or Python set up. Often there's a little hiccups along the way, so please don't wait till the last minute. Get it done early. That way you have a chance to ask the TA or myself some questions to get things sorted out. All right, see you guys soon.